Okay, thank you very much to the organizers for letting me speak. So I'm a second year PhD student at the University of Washington. This is ongoing work, very much ongoing work with my advisor, Dan Mikulincer. Katerina talked a little bit about this yesterday. She gave a really wonderful introduction to what I'm going to be speaking about. So the starting point of this work is Caffarelli's contraction theorem. So what this tells you is given, Gaussian as a source, standard Gaussian as a source, and then a strongly log concave target, the optimal transport map is one Lipschitz. And why would someone care about Lipschitz optimal transport maps? Well, one application is you can transfer functional inequalities. So if the optimal transport map from a Gaussian to some measure nu is L Lipschitz, then we automatically get a Poincare inequality for nu. So you write the variance with respect to nu. You can write that in terms of variance with respect to the Gaussian, use the Gaussian Poincare inequality, chain rule out, and then bound by the Lipschitz constant. And one thing we can notice is that nowhere here in this transference of functional inequalities, this also works for Sobolev and Talleyrand, have we used the optimality of T. So this has sort of, it would be really nice to extend Caffarelli's theorem beyond strongly log concave measures. So there's a lot of work has been done trying to extend it. So for example, but extending is really hard. So for example, Kolesnikov in 11 extended this to log concave target measures which are log concave with bounded diameter, but then the proof is that T is there's a dimension dependence square root n r times square root n Lipschitz, and then you can have a bounded perturbation of the Gaussian, but then here with the perturbation bound being m, you have this double exponential e to the m Lipschitz. T is e to the m Lipschitz. And of course, and using the application of the transference of functional inequalities, we didn't use nothing required the optimality of the transport map. There's been recent work by Dan and Yair, wonderful work saying that this other transport map that Katerina mentioned yesterday, the Kim-Millman one, which arises as a time reversal of like Ornstein-Uhlenbeck process, it gives this transport map gives sharp Lipschitz constants for the above, and then also other target measures like Gaussian mixtures. A lesser known application of this Lipschitz mass transport is comes from this paper of Millman in 15. So if T is a transport map between mu and mu prime, and it's Lipschitz with respect to Riemannian distances, so these we're working on metric measure spaces here, then you get nice, for all I, nice eigenvalue comparison estimates for the weighted Laplacian. Okay. So it turns out you can't really do, these things might not exist if your manifold here, like M and M prime are, for example, like there's counterexamples where M is Euclidean space, M prime is the sphere. But that led Millman to conjecture the following. So first, I want to talk about this definition of a CDK space or a Bakry-Emery condition on a space. So a metric measure space satisfies CDK rho infinity if the Ricci curvature plus the Riemannian Hessian of the here, this is the potential with respect to the volume, is greater than rho times G. So it satisfies Bakary-Emery if this holds. And so an example is, if the metric is the Euclidean one, and then mu is strongly log concave, this satisfies CD alpha. Okay, and his conjecture is that for the source with the Euclidean metric and Gaussian measure, and the target satisfies CD rho infinity. Here, this Gaussian is with covariance 1 over rho times the identity. There is some transport map that transports your Gaussian to mu, and then it's Lipschitz in the Riemannian distances. So you can ask questions like, if we fix mu to be log concave, can we find a metric? Oh, this is a hard problem, this conjecture. You can consider like the following subproblem. So if we fix mu to be log concave, can we find a metric that makes the optimal transport map, in particular, from Gaussian space to RNG mu, a contraction? And we have the following. So this is a dimension 1 result. So if mu is log concave, and we can we can take the Hessian metric, just the metric to be the second derivative of the potential. The optimal transport map, satisfies this. We have a contraction. And the proof is just inspired by Caffarelli's original maximum principle proof, but a little bit more involved. So we can differentiate the Monge-Ampere equation twice for the optimal transport map, and then assume that this term, which is exactly what we want to bound, attains a maximum at some point. We get first and second order optimality conditions, and we combine this with the CDK condition. So the second order optimality condition gives a bound on this term in terms of like the fourth derivative of W. The CD rho condition gives a lower bound for that fourth derivative of W. We plug that in, and this basically cancels everything out here, and so we exactly get that this Lipschitz, the Riemannian Lipschitz constant is bounded by 1. Okay, and then this is just a technical detail to check. A finite differences argument is required to show that this still works even without the maximum assumption. In higher dimensions, we need specific Ricci curvature lower bounds because of the CD rho condition, but and we want to avoid that. So in higher dimension, we're considering the following. So the CDK condition gave a lower bound for the fourth derivative of the potential. It turns out these log concave measures that have a log concave moment measure, so the push forward of the measure by the gradient of the potential is log concave. So if we assume that, then by the result of Kolesnikov, the Hessian metrics for these measures give CD 1/2 spaces, but even without the CD, without even this, there's still a fourth derivative lower bound that you can obtain from the moment measure being log concave. So this is quite promising for higher dimension. And then also something we're considering is how the Kim-Millman transport map relates to the Riemannian sort of Lipschitz constant that we're considering. Yeah, so thank you.